All right, in section 5.3, we're going to talk about a couple new concepts, one of independent, about the product rule, about conditional probability, some different things, finishing up our theoretical probability. So independence is a really important term in statistics. It's up there with mutual exclusive as one of the more important topics in probability. But independence is when two events are said to be independent if one occurring does not change the chance of the other one occurring. Now, we'll get a little more formal definition of this later on and some actual mathematics that we can prove when two events are independent. But very generically, if they're independent, one is not going to influence the other. So if you look at some of these different events, we can see if they're independent. For example, drawing a queen from a deck, replacing it, and then drawing another queen. Well, these are independent because the chances of getting a queen does not change. The key word in there is replacing it, because there's 4 queens out of 52 cards, and if I take one out and put it back, it's still the same chance. Now, getting an A in zoology and getting an A in biology, assuming those are different subjects, we could also say those are independent. Now, if you consider that they're both sciences and maybe they have something to do with each other, you might say they're dependent. But in general, since they're different classes, we'll say they're independent. Now, being a Republican and liking football, those two things really don't have anything in common. So those definitely. So we'll say those are independent as well. Now, this one says drawing a king from a deck and then drawing an ace without replacing it. Well, these would be dependent, because if I take a king out of the deck, so typically there's 52 cards, and the chances of getting the king is 4 out of 52. But if I take a card out, then the chances of getting that ace are 4 out of 51. While as if that event before hadn't occurred, it would still be 4 out of 52. So those are dependent when one influences the other. Now, why we really care about independence is we can use what's called the multiplication rule if we have independent events. So just like in 5.2 when we did addition, you could add probabilities together if you had an or. As long as they were mutually exclusive, you can do the same thing for multiplication and events that are called and. So the multiplication rule says for independent events, the probability that A and B both occur is the probability of A times the probability of B. Now, this is the intersection symbol, the upside down U. That just means and. So essentially, we want two things to occur. So I want to draw an ace, and then I want to draw a king. I want to roll a 2 on a dice, and then I want to flip a head. All these things are different things where it would be and. But this obviously only counts if they are independent. So let's look at a couple examples. So this says the probability of drawing an ace and then drawing a second ace from the deck, assuming we replace the card. Well, since we replaced the card, these are independent events, and that's a very important thing. So the way I would write this is I would say, what's the probability of drawing an ace and then drawing another ace? So the probability of drawing an ace and an ace. Now, since we put it back, this is simply going to be the probability of drawing an ace times the probability of drawing an ace. Now, there are 4 aces in the deck out of 52 cards, and that is the same for both of these. Now, you can multiply it and then reduce, but I think it's easier to reduce these fractions first, and 4 does divide into 52. This becomes 1 out of 13, so this would become 1 out of 13. You can reduce it later, but it's always easier to reduce before you multiply. So that'll be 1 out of 169. So the probability of getting 2 aces, assuming you put them back, is 1 out of 169. Now this next one is a more generic problem. It says if 78% of math students love math, what is the probability 3 randomly selected students all love math? Well, these would also be independent because the way you feel about math is not really going to influence how someone else feels about math. So if I want the probability that 3 people love math, it's the first one loves math, and the second one loves math, and the third one loves math. Well, since these are independent, because one doesn't really influence the other, this is just the probability that each one loves math. And since we're saying the generic probability for anyone loving math is 78, this is just going to be 0.78 times 0.78 times 0.78. And since these are just decimals, I'll just multiply them. 0.78 to the third power is going to be 0.4746. So about a 47.46% chance that if there's a 78% chance a random student loves math, that 3 of them would love math. Now this one's a really pretty easy one. A harder question would be that we'll eventually talk about is what is the chances that 2 out of the 3 would love math or 1 out of the 3 would love math. That would be a little harder. So if things are independent, a lot of times what you'll deal with is what's called conditional probability. So conditional probability is trying to find probability when something has already occurred. So we say it's the probability of an event occurring if another one has already occurred. And we have new notation for this. When we say this, you could say the probability of A with a line B. This is read the probability of A given B has occurred. So B already happened. B has already happened. That cannot be changed. So what's the probability of A happening now? So that is conditional probability. There is a formula that we have for conditional probability, but before we get to that, we're just going to kind of talk about it informally, and we'll do this in the form of a chart. So here's a table that takes 2 pieces of information. It says how satisfied people are with their job, satisfied, not satisfied, or undecided, and then what career they're in, one of these 3. And then the table basically will say how many are in both categories. So there are 100 people that are satisfied with their job and in the education field. So these tables are really nice things to do. We could total up how many are in each one, 450, 450, I believe that's 180, 200, 360, so that would have to be 520. So if I add the columns or the rows, I should get the same number, and I do. That's 1,080. So I'm going to define a couple events. I'm going to say event A is a person is not satisfied with their job, and event B is a person is in sales. So when I ask the question, the probability of A, this is the probability someone is not satisfied in their job. Well, if I look at this, how many people are not satisfied in their job? Well, that would be 450. And how many total people are there? There are 1080. So that reduces to 45 over 108. And let's divide by 9, so that would be 5 over 12. So that's a pretty traditional probability using the table. It's how many were not satisfied out of the total number. Now let's look at the next one. This is the probability of A given B. Now this is going to be a little trickier. So let's write what we actually mean. This is the probability that someone is not satisfied given they are a salesperson. So what we know is this person is in sales. They are already a salesperson. So if I know they are a salesperson, then I'm only really looking at this row of people because I already know this individual is in sales. So the probability of someone not being satisfied with their job given they're in sales is 300 out of 520. Now, why is that true? Well, we're only looking at the people that are in sales, because everyone else we don't care about because we already know this person's in sales. Because when you have this line and whatever comes next, we know that's already occurred. So that reduces to 30 over 52. That reduces to 15 over 26. Now this next one looks similar to the one we just did, but it's actually backwards. The B comes first and the A comes second. So this is going to be the probability that someone is in sales given they're not satisfied with their job. So if we look at the people that are not satisfied, now we're just looking at this people in this column because we know the person is not satisfied. That's already given to us in our problem. So I'm only looking at the 450 people there. So how many of those 450 people are in sales? Well, it's 300. So 300 out of 450 is just 2/3. So when you have the given condition, you're not looking at everyone in the population or in your data set. You're only looking at a certain subgroup because something has already happened. All right, so the nice thing is we can do it with a table. Sometimes we don't want to do it with a table. Sometimes we like to have a rule. So there actually is a formula for conditional probability. The probability of B given A is the probability that both of these events occur divided by the probability of A. Similarly, if I want to do the probability of A given B, it's the probability of A and B, so both occurring, divided by the probability of B. So we can use this problem on different ones without the formula, but some you have to use the formula. Like this one, it says, according to the U.S. Census, 19.1% of U.S. households are in the Northeast. So that's pretty important information. And 4.4% of U.S. households earn more than $750,000 are also located in the Northeast. Determine the probability that a randomly selected U.S. household earns more than $7,500 given it's from the Northeast. So what I'm trying to find is I'm trying to find the probability that someone earns more than $75,000 given they're from the Northeast. So if I use the formula, this is going to be the probability someone earns more than $75,000 and is from the Northeast divided by the probability someone is from the Northeast. And that's just using our whole probability that A given B is the probability of A and B divided by the probability of B. So if I look at these percentages, the probability that they earn more than $75,000 and in the Northeast are 0.044, and the probability they're in the Northeast is 0.191. So if I calculate this, this will turn out to be 0.23-ish. So there's a 23% chance that if you are from New England, you make $75,000 or more, but that is a given condition. So we actually use this to kind of, this whole conditional probability formula, we use this to kind of come up with what's called the general multiplication rule. Because not all events are independent, some are dependent. So if we do a little algebraic manipulation, we can figure out that the probability of A and B, and again, there's that upside down U, A and B, is the probability of A times the probability of B given A has already occurred. So probability of two things happening is the probability of the first times the probability of the second, assuming the other one has already occurred, which kind of makes sense. We have to take that into consideration because it's already happened. So let's look at some examples, and you can always look at the, you can always use the general multiplication rule. Sometimes it goes to the nice generic one with independent events, but it works for either one. So if we look at this one, it says a card is drawn from a deck and replaced, and then a second card is drawn, and what's the probability of getting a queen and then an ace? So these are independent events, namely because we replace it. But it doesn't matter. If I want to say the probability of getting a queen and then an ace, if I use the generic multiplication rule, it's the probability of queen and times the probability of an ace given a queen was drawn, but then replaced. So the probability of getting a queen is 4 out of 52. But then I put it back, and now the probability of getting an ace, there's 52 cards again, and there's 4 aces. Well, we've had this probability again before. This is 1 over 13 times 1 over 13, which is 1 over 169. So those were independent. Of course, they do not have to be, and we'll see some that aren't. This one says the Harris poll found 46% of Americans say they suffer great stress at least once a week. 3 people are selected at random. What's the chance, the probability that they all will suffer great stress at least once a week? So essentially, this is saying the first person is stressed, and the second person is stressed, and the third person is stressed. But if you're picking 3 random people, that one chance that one is stressed should not influence the other one being stressed. So this is just the probability the first one is stressed times the second one being stressed times the third one being stressed. And so that probability is going to say the same for all of these, 0.46, 0.46, 0.46. So these are independent. So we just multiply them. And if they weren't independent, there's really no way that you could figure out the probability of the conditional probability from that. So in general, if they give you a probability, it's generally independent. So let's look at this next example where we'll have some that are dependent. And the reason these are dependent, we're drawing cards again, and we're not replacing them. So once something has happened, it's kind of permanent. So this first one says, what's the probability of getting 3 jacks? So if we think about this, the probability of getting my first jack is going to be 4 out of 52. That's kind of generic what we think about, right? But now we're going to multiply the probability of getting another jack, assuming we've already gotten one. So we've already gotten 1 jack, so that's happened because we're not replacing it. So there are only 51 cards, and there are only 3 jacks left because there are only 4 in the deck. We've already drawn 1, so there should only be 3 left. And then 2 out of 50 because there's only 2 jacks left and only 50 cards, so each time it goes down. So we can reduce these. These are 1 out of 13. This is 1 out of 17. This is 1 out of 25. So if you multiply across, that's 1 out of 552, I believe. So the only difference in this independence is we have to make sure we consider what has happened previous, because that is going to influence what is going on. All right, so the next one says, what's the probability of getting an ace, and then a king, and then a queen? And the big thing is they're still not replaced. So there are 4 out of 52 for the ace. That doesn't really change. Now for the king, if I look in the deck, I've already got an ace, but there are still 4 kings left. The only difference is there's only 51 cards left. So the numerator doesn't change, but the denominator does. And then I want a queen in this order, so that's going to be 4 over 50. And we say in this order because it actually does change if you want to do slightly different draws, getting different cards first. So we have 4 out of 52, 4 out of 51, and 4 out of 50. So if I reduce and multiply, this one is going to become 16 over 33,150. So my guess is this is something you don't want to bet on because this is not a very likely scenario. C says, what's the probability of getting a club, and then a spade, and then a heart in that order? Well, there are 4 suits, and there are 13 in each suit. So if you're saying the probability of a club, there are 13 clubs out of the 52. There are 13 spades as well, but there are only 51 cards left for the second draw, because remember, we're not replacing. And there are 13 hearts, but there are only 50 cards because we've taken out 2. So let's see, that reduces to 1 over 13, so this should be 169 on the top. And the bottom, I believe, is 10,200, I believe. All right, finally, we want to get 3 clubs. So we want to get a club and a club and a club. And again, remember, we're still putting the cards, not putting the cards back. So 13 out of 52, that's fine. That doesn't change much from the previous problem. But now we want another club. Well, there are only 12 clubs left because I've already pulled one out. We're assuming given that's already occurred. Times 51, and then 11 out of 50. So this is 1/4, so this would be 132 over 10,200. And again, I just reduced this one to 1/4 and did the multiplication. You can just put it in your calculator, it would be fine. And let's see, that reduces to 22 over 1,700, which I believe is 11 over 850. All right, let's look at one more. It says, if the Michigan Wolverine football team wins 20% of the game, what's the probability they will win 5 games in a row? What's the probability they will lose 5 games in a row? Now, in general, a football game is independent. The chance of one thing occurring doesn't really influence the other. So the probability of getting 5 wins in a row would be 0.2 times itself 5 times, because the probability is the same because these are independent events. So 0.2 times itself 5 times, which is 0.2 to the 5th, which is 0.00032. So not a very good chance of winning 5 games in a row. We can also do 5 losses in a row. The only difference is the probability of losing a game is 0.8. So this would just be 0.8 to the 5th power, which is going to be 0.32768. Now, these were pretty easy problems because they stay the same. Harder problems would be, what's the chance you win 2 out of the 5 or 3 out of the 5? Those are going to be a little more complicated, and we'll have to look at those later down the line. Now, all the chance events we've looked at so far have been pretty elementary, but some have a lot of different outcomes that we have to kind of consider. So in those cases, sometimes we will use what's called a tree diagram. Now, a tree diagram is going to be a method to find all outcomes and their probabilities. So we're going to see all the different things that can happen in a chance event and what those probabilities are. So let's look at an example. So this first example is a pretty easy one. We are going to flip 3 coins. We want to know what's the probability of it getting at least 2 heads. So when I flip 3 coins, I'm going to do each outcome first. So if I flip a coin, I'm going to get either a head or a tail. So a tree diagram kind of goes like this, head or tail. Now in each branch, there's a half chance I get a head and a half chance I get a tail. Now if I flip again, it is independent essentially of what happened on the first turn. So I could get a head or tail again, half chance here, half chance here. Or I could get a head or tail assuming I got a tail on the first flip, so half and half. And then again, if I go for a third flip, it doesn't really matter what happened on the first 2. I could get a head or a tail following any of these branches. And these would all be half as well. Half, half, half. Now, if we take any of these halves and add them up, it's obviously bigger than 1, which we can't have. But when we think about the outcomes in all 3 flips, it actually is not. So the outcomes now are just the branches of this tree. So here is one branch. It could have all 3 heads. And the probability of getting of all 3 heads is 1/2 times 1/2 times 1/2, which is 1/2 to the 3rd power. So since we're doing head and head and head, we multiply along those branches. So 1/2 to the 3rd is 1/8. This next branch is HHT, which will also have a probability of 1/8. And then HTH, that would be going this way, and that's 1/8. They don't always have to be the same. In this example, they're all basically the same. They're all 1/8, 1/8. Tailhead head is 1/8. Tailhead tail is 1/8. Tail head is 1/8. And all tails is also 1/8. So now if you add up all these 1/8s, you essentially have 1/8 8 times, which is 1. Which is what you should have, because something should happen. Now, if I want to answer the question using this tree diagram, it's pretty simple. It says, what's the probability of getting at least 2 heads? Well, at least 2 heads means 2 or more. So this would be 2 or more heads, this would be 2 or more heads, this would be 2 or more heads, and this would be 2 or more heads. So the probability of getting at least 2 heads is going to be one of these, but it's one of those added together. So it's 1/8 plus 1/8 plus 1/8 plus 1/8. So it's 4/8 or 1/2. So when you're going with the branches, you're just multiplying, but when you're actually adding the different outcomes together, we add them. Let's look at another example where we set up a tree diagram. It says the researcher finds that 93% of teens use the internet and 55% of online teens have a social network profile. What's the probability a randomly selected teen is online and has a profile? So we'll go ahead and make our tree diagram. So they're either going to use the internet or they're not going to use the internet. And it says that 93% use the internet. That means 7% don't, because they either have to do one or the other. Now it says if you're on the internet, you're either going to have a profile or not have a profile. And if you're not on the internet, you're going to have a profile or not have a profile. Well, if you're on the internet, the chance you have a profile, it's given in the problem, is 55%. So the probability you don't have a profile is 45%. Now, if you look at the bottom branch, it says if you're not on the internet, what's the chance you have a profile? Well, there's 0 chance, because if you're not on the internet, you're not going to have a profile on an internet site. And the chance you will have not a profile is 100%. So now, if I want to take these outcomes, I could be on the internet with a profile, I could be on the internet with no profile, I cannot be on the internet with a profile, and I cannot be on the internet and not have a profile. Now the easiest one is, of course, this one, because it's 0, because 0.07 times 0 is 0. 1 times 0.07 is 0.07. Internet and a profile would be 0.93 times 0.55, which should be 0.5115. And then 0.93 times 0.45 for that branch is going to be 0.4185. So if I add these 4 numbers together, I should get 100%, because that's the chance. So this one says, what's the probability a randomly selected teen is online and has a profile? So they're online, they're on the internet, and they have a profile. So that would just be this probability here. So the probability they're on the internet and have a profile is 0.5115. Now we could have done this without doing the tree diagram, but now you can do lots of things with this once you have your numbers. In this case, we just wanted this one basic one both occurring, but in other cases like the previous one, we could add them up and do different things. Let's look at one more tree diagram. It says an insurance company classifies drivers as low risk, medium risk, or high risk. So I'm going to break them down into high risk, medium risk, and low risk. And it says 10% of drivers are high risk, and 30% are medium risk, and 60% are low risk. And then the high risk drivers, you're either going to have an accident or not have an accident. You're either going to have an accident or not an accident if you're a medium risk, and an accident and not an accident if you're a low risk. And then all these probabilities are given. It says if you're a high-risk driver, there's a 9% chance you'll be in an accident, which means there is a 91% chance you won't. If you're a medium risk driver, it says there's a 5% chance you'll be in an accident, which means there's a 95% chance you won't. 1% chance for low, so 99% chance for not an accident. So our outcomes here are going to be, it's going to be high risk in an accident, high risk not in an accident. Well, this would just be 0.1 times 0.09, which is 0.009. This one would be 0.10 times 0.91, which is going to be 0.091. So for the medium, it's either a medium in an accident or a medium not in an accident. 0.30 here times 0.05. And this one's going to be 0.3 times 0.95. So that's going to give me 0.015 and 0.285. And then low with an accident and low with not an accident, I'll multiply their probabilities. 0.6 times 0.01, 0.60 times 0.99. So those are going to be 0.006 and 0.594. So those are the probabilities of every single outcome that could happen in this scenario. Now, what we're trying to ask, though, if you recall from the problem, it says, what's the probability that they'll be in an accident? So we're really trying to figure out how they'll be in an accident. So everyone who's been in an accident is going to be included in this set. So that would be this one, and this one, and this one. So the probability you're involved in an accident is this 0.009 for the high risk, and 0.015 for the medium risk, and 0.006 for the low risk. So if I add that up, I get 0.030, so 3%. So making these tree diagrams can be really, really helpful because it really helps you see all the outcomes and you can find the probability of each of them occurring.